All right, hello everyone. I am Marcus Hodges. I am a security partner at Meta, and I support our Augmented Reality division. And today I'm going to be talking with you about meaningful hardware privacy features. So there are many smart home, wearable, and virtual reality devices on the market today. And augmented reality products are emerging. We have smart speakers with cameras and conversational voice assistants in our living rooms, and virtual reality devices feature a range of sensors for immersive experiences. Wearable devices, such as Ray-Ban Stories, are the forerunner to the augmented reality glasses of the future. But with these new technologies come new security and privacy risks. These devices have a lot of sensors that in some cases are always on. They may be permanent fixtures of our living rooms or home offices or something we take with us everywhere we go. And there are many private and semi-private spaces in the world that we need to consider, such as public restrooms, medical clinics, daycares, and many more, where people have a strong expectation of privacy in these private spaces. And we need to consider many risks, including those of malware and inauthentic applications with excessive permissions. So to help mitigate some of these risks, there are two emerging hardware privacy features that are becoming increasingly important. The first of these is the sensor mute switch, which disables sensors such as the cameras and microphones on your device. And it's effectively a manual override that gives the user direct control over the sensors and experiences. The second is the record indication LED. This LED indicates to users and bystanders when cameras or microphones or other sensors are actively recording. Now, the color of this LED, its blink pattern, and what exactly it's indicating depends upon the device. And as we'll see later, its exact meaning is deceptively simple. So today, I'm going to talk about how these features are designed, what makes them secure, and I'll explain why augmented reality is going to make everything more complicated. So to start, it's helpful to consider the levels of trust in platform security. User applications have the least amount of trust, arguably untrusted. And hardware has the most trust, but there is a gradient in between, which includes the operating system kernel and firmware and other elements. Now, we say that a system provides hardware security assurance if it is immutable and isolated. Immutability is a unique property of hardware, and this is what makes the initial boot ROM secure and makes secure boot possible. Immutability and hardware security assurance will protect against software attacks at all privilege levels, including a compromised operating system or firmware, but there is a catch. Systems that are immutable cannot be updated, and so they need to be simple, effective, and easy to validate. The design of the sensor mute switch begins with a fundamental question. How do you disable a sensor? Now, the first and most obvious approach is to simply turn off the power. But if it were that easy, I wouldn't be standing here right now. So let's look at a typical camera sensor and consider the option space. Every electrical component, including sensors like cameras and microphones, have what is called a pinout. A pinout is the diagram of the electrical connections that are used to power and communicate with the sensor. Now, it doesn't matter if these pins are actually pins or if they're wires or if they're traces buried deep in a circuit board. This is simply the electrical API. Now, this is the pinout for a simple camera sensor, and as you can see, we have pins for power, clock, reset, ground, and there are sets of pins for the MIPI and I2C data buses. Now, I said before, you can't simply cut the power to a sensor, and this is because severing power suddenly can cause voltage spikes and other really bad electrical phenomena to happen, which is why in practice when we're designing hardware, components are usually powered with something called a PMIC, or a power management integrated circuit, that brings voltage and power up and down smoothly, gracefully. And the other thing to keep in mind about power is that there could be a single power rail traversing a system that lots of components are connected to. And disabling the power might disable a sensor, but it might disable half of the system with it. So you may not have individual control over power the way you would perhaps assume or expect or want. Now, the real goal of disabling a sensor isn't exactly to power it off per se. What we're trying to accomplish is the prevention of flow of data to protect privacy. So one thing we can consider is to turn off the data wires. Now, most electrical buses have many wires that operate together so that bits of data can be transmitted in parallel. So disabling an electrical bus means putting a gate or a transistor on each of these wires so we can turn them off simultaneously. And this increases complexity. Also, these high-speed transmission wires for data are often very sensitive to changes in electrical properties like impedance. So it's not so simple to simply turn them off and add components in the middle. Now, there are a lot of sensors in the world, and, there may also be more than one data bus in a system. So in this particular case, we have the MIPI data bus at the top, and this is where the pixels of an image are transmit, so the bits of data actually flow over the MIPI bus. But the I2C data bus is used for command and control, for sending commands to the camera, for like setting the aperture, frame rate, resolution, starting the capture of a video or something like this. And so we might have to turn off more than one data bus, and this also increases complexity. And suddenly severing data connections, a lot like disabling the power, suddenly can have unintended side effects, especially on firmware that might be in the middle of some communication. You know, this is a little bit like cutting a phone line in the middle of a conversation. So in our exploration, we discovered that holding cameras in reset is by far the best way to disable a camera sensor. The reset pin is effectively equivalent to rebooting the device and holding it in the rebooted state. And this is a very effective way to disable a camera sensor, and it also has the benefit of being a single wire solution. Now let's look at the microphone for a bit. The microphone typically has a very simple pinout that includes 4 wires: power, clock, data, and ground. PDM microphones use the input clock signal to modulate sound, which is then transmitted out the data line. In our research, we discovered that certain microphone manufacturers actually have enough internal voltage bleed from the clock signal to sufficiently power the sensor and get data off of it, even if you completely cut the power. And this is somewhat surprising, and once again we find that powering off the device is not the most secure or private option. So in this case, we recommend gating the clock or the data or both. Now let's look at a couple of examples of these features in the wild. Apple's MacBooks and other Apple products feature a hardware microphone disconnect, which is built into the lid. And this lid of your device acts as a switch so that when the lid is closed, the microphone is disabled purely in hardware. Now, this is resilient to software attacks at all privilege levels, including a compromised operating system, so that those compromised pieces of software could not gain access to your microphone with the lid of your MacBook closed. And it also turns out that with the lid closed, the camera's field of view is completely obstructed. So you get that for free, which is great. Amazon Smart Speaker is another great example of a device that has a mute switch with hardware security assurance. In their design, the button switches power between the microphone and a red LED so that only one can have power at a time. And this is elegant. But note the use of a button instead of a switch requires that you have an LED so you can tell what state the system is in, whether the sensors are on or off. And this is important not to conflate this particular LED with the record indication LED we'll talk about in a minute. So let's talk about the full system design. If you have a single camera microphone you want to disable, wiring it to the switch is more or less straightforward. Now, if you have many cameras and sensors you want to disable with the mute switch, you can daisy chain them like I have in this design, but this has many drawbacks. First, you need to notify the operating system, device drivers, and other components that you're about to shut off sensors before they suddenly disappear. And second, there are many sensors in the world, and it's not always straightforward to know exactly which ones you should turn off. It turns out that IMUs, or inertial management units, are often sensitive enough to record audio. And temperature sensors can be used to monitor certain health characteristics. But disabling a temperature sensor could render a device extremely unsafe for the user. And so there are a lot of trade-offs to be considered. And that might also impact usability a lot, disabling the sensors. These devices do not have keyboards or mice for user input. So all of the interaction you have with them comes in via the sensors. Smart speakers are a good example of this. If you turn off the microphone to a smart speaker, you can't communicate and interact with that device at that point in time, which is to some extent the point, but you need to think about the impact on usability when you're making these decisions. So it is a desirable property to preserve optionality in your hardware design until later in the manufacturing process. But when you think about preserving optionality, this is actually completely at odds with the concept of hardware security assurance and immutability. So one thing we can do is to include a one-time programmable microcontroller like a CPLD. Now, the one-time programmability of certain microcontrollers allows you to have late binding optionality over the logic and sensors, and which sensors might be disabled. And it still provides hardware security assurance because once it's programmed, it's immutable from then forward. Now, the inclusion of a microcontroller logic like this also allows you to implement a time delay so that you can notify the operating system and drivers before you bring the sensors down hard. There is a downside of this design, though, is that it takes up a lot of physical space, especially if you have one wire for every camera. And if you have a dozen cameras, that's a dozen traces on your circuit board, and that may not be space you have, especially in a constrained form factor like a pair of glasses. So one way we can address some of these challenges is by taking the design and moving it into custom silicon inside the system on a chip. In this design, the switch is wired directly to our system on a chip and routed internally to two places. The first is an uninterruptible timer, which delays for a few hundred milliseconds and then shuts down the sensors. The second is the root of trust, or firmware in the root of trust, which becomes the system that is responsible for notifying the operating system and bringing the sensors and related components down cleanly and smoothly before they get disabled in hardware suddenly. In this design, instead of holding the cameras themselves in reset to disable them, what we're doing is holding the C-Fi receivers inside the chip in reset. It's the same technique to disable the sensor, but we're doing it internally instead of externally. Now, the C-Fi receivers are the component that the cameras are wired directly to. And so disabling them is as effective as disabling the camera, but it takes up considerably less space. But like everything, this also has a downside. Or before I talk about the downside, turning off the C-Fi receiver is a little bit like me turning off my cell phone so you can't call me, using the phone analogy again. So the downside of this is that it's very difficult for an external researcher to validate. It's custom silicon. It's very small. Not impossible, but it raises the bar a lot. And I do consider that a downside. All right, let's shift our attention from the mute switch that disables sensors to the record indication LED that tells you when things are actively recording. Now, the Ray-Ban Stories LED is hardwired directly to the camera sensor power. If the camera is powered on, the LED is on, and vice versa. This is simple, it's easy to understand, and it provides robust hardware security assurance. But I'd like you to note a very subtle difference between a camera being powered on and a camera actively recording. Electrically, active recording might be a little bit more akin to there's bits of data flowing off of the sensor over a shared bus. But monitoring that bus to see if data is being transmitted and somehow or another wiring an LED to that not only would be incredibly difficult, but you probably couldn't do this with any security assurance at all. So the implication of this particular design is you actually have to turn off the cameras or power them off when they're not actively in use. Otherwise, the light would be on all the time. Now, Amazon Smart Speaker takes an entirely different approach. The microphone is normally on and listening for a wake word. Phrases like, "Hey Alexa." I'm waiting for somebody's device to go off. I always do that on purpose. So it's listening for a wake word, right? But the light is actually off that entire time. And the light only comes on once a wake word is detected and data starts streaming to the cloud. Now, as you may have guessed, this would be very difficult to design with hardware security assurance. This is a higher order concept, wake word processing. But it does provide certain restricted functionality gives it the ability to access sensor data, again, without that light being on all of the time. And this is an important and admirable quality for several reasons. Now, as we know, wake words are probabilistic. And we all have firsthand experiences where these devices have been activated accidentally. So this is a good example of how the privacy or the sensor mute switch and the record indication hardware LED actually complement each other really nicely as features. They go well together. When we get to augmented reality, the world gets more complicated. In addition to the cameras and microphones that will be there so the user can capture photos and videos of their experience and share them with their friends and family, there are going to be many cameras and sensors for all sorts of environmental processing. There'll be cameras and sensors for mapping your spatial environment and detecting your location within that space. And they'll be, because remember, these devices do not have keyboards or mice, so all of the user input comes in via these sensors. So you'll probably have sensors or cameras for hand tracking for user input or monitoring your eye location so it knows, where you're looking for user input, right? And just a wide variety of sensors. Microphones will be used for hands-free voice control and dictation. So let me ask you the question. Now what does this LED mean? Does it mean that sensors or cameras are on? Which cameras? For what purpose? And this brings me to the concept or the issue of LED semantics. What does the LED mean? That sensors are on? Powered on? Which sensors? Does it mean they're actively recording? And does that mean that data is flowing like bits from the sensors, or the data is streaming to the cloud? Or the data is persisted somewhere such that it may be accessible to the user or the provider? And do we want this LED on for machine perception, such as wake words or spatial mapping or hand tracking or computer vision tasks? And to answer these questions, we need to consider very carefully all of the privacy implications of these things. Is a feature always on, processing in the background, or is it user activated? Is the data being processed ephemerally? Is it processed in a secure enclave? How high of fidelity is the data or the derivation of the data? And how is it being used? You know, if this light is on all of the time, it will quickly lead to alert fatigue, and it'll become less meaningful. But where do we draw the line? So today I want to leave you with a few takeaways and a call to action, and perhaps more questions than answers. So today I explained how to design a sensor mute switch with hardware security assurance that's robust and meaningful. But hardware is hard, and it takes a significant investment in security and privacy to design and build features like this. We also saw that this LED has complicated semantics that are already overloaded and mean many different things. And when we get to augmented reality, this is going to become even more problematic. So we need to come together as an industry to align on standards to ensure that these hardware privacy features continue to be secure and meaningful. And now I'd also like to point out that it is a particularly good time right now to be researching these topics and these open questions. There's a good opportunity here to influence the industry of how these things are designed and what they're for. So I invite all of you in your research to consider these things, tear down these devices, submit, to our bug bounty program. And as a reminder, we also have an annual, Meta publishes an annual RFP for research in security and privacy topics for trustworthy AR and VR products. So look for that and invite you all to participate. And I thank you for your time. Any questions?